In this video, I'm going to go over alkene reaction practice problems. So we're going to go over 5 practice problems related to the alkene reactions. So first, pause the video and try these questions first, and then resume the video for the walkthrough of these answers. So for the first question, we see that we have a cyclohexane with an ether onto the cyclohexane with HCl and methanol. So first, we see that we have a HCl acid, which means that we're going to look for our most basic atom to do an acid-base reaction. Our most basic atom in this case is this oxygen with its 2 lone pairs of electrons, where it's going to grab the hydrogen from the HCl and kick off the chlorine group and give us this protonated structure. Now we formed a good leaving group where our carbons holding the oxygen in the ether are more electrophilic, and we have 2 competing nucleophiles now, the chlorine ion or the methanol. Now you might be thinking that the chlorine minus is a stronger nucleophile than the neutral methanol, but in this case you can think of the methanol as the solvent, and if it's a solvent, then there are millions more times methanol than chlorine is, overpowering the chlorine ion nucleophile. So in this case, our nucleophile is the methanol. So in this case, this methanol is going to either attack either carbon in the SN2-like fashion, doing a backside attack, and kicking up the leaving group on the other carbon. So in this case, I chose that carbon, so I'm going to draw this. And since this is an SN2-like reaction, the other bond has to be opposite in stereochemistry. So if this is a dashed OH, then the methanol would have to be attached to a wedge to the cyclohexanol. So that oxygen of the methanol attacked that carbon, which is why this is the new bond between the oxygen and carbon. And this oxygen is attached to a methyl group and the hydrogen group, giving it a positive charge. And then Cl minus ion could come in and deprotonate this oxygen here, giving us our final product. OCH3 plus enantiomer, because we could have put the OH as a wedge and the OCH3 as a dash. Now let's move on to the next problem. We see that we have HCl again, so we're going to look for our most basic atom, which is going to be one of these carbons of the alkene. So how do we tell which carbon do we choose from the alkene to grab the hydrogen? Well, we're going to choose the one that is going to form the most stable carbocation. So we see that this carbon here is going to form the most carbocation, so we're going to have to grab the hydrogen on the other side of the alkene, which is this carbon over here, because we want the carbocation intermediate to lose the bond. So the other carbon is going to grab the hydrogen, kick out the chlorine, and then give us this carbocation over here. Because this carbon lost the bond, this carbon still has its 4 bonds, and then we bring in our chlorine minus ion. And before we do this, since we formed a carbocation, we always have to look for hydride shifts, which could be like a hydrogen, or we could look for a methyl shift, which is a methyl group moving to form a more stable carbocation. So we see here to the right of this carbocation, we could do a methyl shift by moving one of these methyl groups onto that carbocation to form a tertiary carbocation instead of a secondary carbocation. So I'm going to draw it like this. Now we have a carbocation on this tertiary position, which is more stable. And then we bring in our chlorine minus ion to attack that carbocation, and this will give us our products. And since this is a SN1 reaction, this is a sp2 carbon, the chlorine could either attack on the top side, giving us a wedge, or the bottom side, giving us a dash. So let's say it's a wedge, and the other method will give us a dash. We could do plus enantiomer. But in this case, we don't have to include wedges or dashes because this is not a chiral center. Because this carbon has two methyl groups, so we could just leave it as planar for all of them. So we have this and then chlorine right there. And that's our final answer. So now let's move on to the next problem. We see that we have an alkene with a halogen X2 and a solvent H2O. So I'm going to go over the mechanism and explain how this works. The alkene is going to attack one of the chlorines of the CO2. And as the alkene is donating electrons, it's losing electrons. And we're going to kick this off. And as it's losing electrons, the chlorine is gaining electrons, making it more negative. The chlorine is going to attack the other side, giving us this chloronium ion intermediate right here. And now we have our Cl minus ion and our water solvent. Like we said earlier, this water solvent is going to overpower the Cl minus ion nucleophile because there are excess solvent compared to the chlorine ion. So then we're going to attack either this carbon or this carbon. So how do we tell which carbon we are going to attack? We are going to attack the one that is going to give us the most stable carbocation intermediate. So what we could do is make that good leave on that side, because we see that this carbon here is going to form a tertiary carbocation, whereas this side here is going to form a primary carbocation. We see that we want a tertiary carbocation instead of a primary carbocation, so that's why we kick the chlorine on the other side right there, making this intermediate right here with a positive charge right there, and then the water is going to attack that carbocation, and then that is going to give us this intermediate right there, and then the Cl minus ion could just come in and deprotonate the positively charged oxygen right there, and that will give us our final answer right here with the Cl attached still right here. Okay, let's move on to the fourth problem now. So we see we have osmonium tetroxide and a hydrogen peroxide with an alkene. So this reaction is going to add vicinal diol, and its stereochemistry is going to be syn addition, which means that the two alcohols are going to be right next to each other and on the same side. So we see that our two carbons here are these two carbons of the alkene. We're going to add them on the same side. Let's say we add it as a wedge. That means the methyl has to be a dash, and the other side would also have to be a wedged alcohol because this is a syn addition, and this would be plus enantiomer because the alcohols could have been a dashed and the methyl could have been a wedged. So now let's move on to the fifth and last problem. We see we have an alkene with O3 and CH32S. This is a ozonolysis reaction. So what I do is I cut the alkene in half and add oxygens at the ends of those alkenes and redraw them as such, like that and like that. We see that this carbon here has a hydrogen and this hydrogen here also has a hydrogen. We could leave it like this as the answer, but to redraw this into a neater way, we could draw it like this. Since this is an aldehyde, we could draw that as CHO, and we see that we have a 1, 2, 3, 4 carbon aldehyde. So we could do that as 1, 2, 3, 4. Make sure that's 4 carbons, 1, 2, 3, 4. So these are our two final answers for this ozonolysis problem.